So in the normal shock, so there is a sudden change in properties. So P naught is not constant across the normal shock. Okay, the P naught 2 is less compared to P naught 1. So P naught is not constant, but we are not heating or cooling the system. So T naught is constant. Okay, this is the one case we have seen. And the next one is Rayleigh flow. So Rayleigh flow means only flow with heat transfer. Okay, that is if there is a duct, there may be a heat addition or heat rejection. Due to that, how this inlet may be the subsonic, supersonic, how it changes, that we are going to study here. And here also, due to that heat dissipation, there will be a stagnation loss across the duct. Okay, so here also P naught is not constant. Again, we are heating or cooling the system, so T naught also not constant. Okay, this is for Rayleigh flow. Okay, for the shock, T naught is constant, but for this Rayleigh flow, as we are adding or removing the heat, T naught also not constant. Then third one, this Fano flow. So this is the only flow with friction. So here, so we will take the long duct and we will see how this inlet property, subsonic or supersonic changes due to this, the frictional wall. Okay, so there will be a friction in this wall. So due to the friction, how this subsonic supersonic flow changes. So here also, due to the viscous effect, there will be a stagnation pressure loss. But here we are not adding or removing any temperature, any heat. So T naught is constant. Here also we have a separate gas table for Rayleigh flow and Fano flow. In addition to that gas table, you should remember these formulas also to solve the problem. Like in the expansion fan, we use this formula, right? Theta is equal to gamma m2 minus gamma m1. Even though we have a gas table, this formula is necessary. Similar to that, in Rayleigh flow also, this Q formula is compulsory to solve the problem. In this Fano flow, this length formula is compulsory. Okay, you should remember this in addition to the gas table. Okay, I will start with this Rayleigh flow now. So I'm taking one constant area duct, okay, and there is a heat addition or heat rejection. Then this will be called Rayleigh flow. As usual, we should start with the three basic governing equations: continuity, momentum, energy. And in this energy equation, you should take the Q also because there is a heat transfer. Okay, and you know the flow is non-isentropic because P naught 1 is different, P naught 2 is different. Always there will be a pressure loss. So Q term will be added because there will be a heat transfer. So then first step, I'm taking this energy equation. So instead of H, I can substitute CPT. Okay, so in this equation, instead of H, I'm substituting CPT, then rearrange, then apply this stagnation condition to this equation. That is, stagnation means velocity will be 0 and T will be T naught 1, T2 will be T naught 2. Then rearrange, you will get Q is equal to Cp T naught 2 minus T naught 1. Is that clear?
Yes, sir.
Okay. So just from the energy equation, apply the stagnation condition. Okay, instead of H it is Cpt. T instead of T it is T naught because of the stagnation. Then rearrange, you'll get this equation. So from this equation we can find the T naught 2 because mostly in the problem they will give this heat transfer value, also the inlet condition T naught 1. Using that you should find what is the T naught 2. Mostly we will use the formula to find the T naught 2. By comparing this T naught 2, T naught 1, if T naught 2 is higher, then there is a heat addition. If T naught 2 is lower than this T naught 1, then there is a heat rejection that you can find it. Okay. The next one we are going to find static properties: pressure, temperature, density, then stagnation property P naught 2, T naught 2, etc. and all. So to find this P2 by P1, So I'm starting with this momentum equation. Okay. So P plus rho V square is equal to constant. That apply here, you will get this equation. But in the final term, I have only gamma m1 and m2. There is no rho term, u term, etc. And we know how to convert this rho u in terms of pm in the diamond aerofoil we have discussed. Okay. So instead of in this rho u term, if you multiply gamma p by gamma p, you will get this term. Then we know gamma p by rho, that is gamma p u square. This gamma p by rho is a square. Okay, then this u square by a square is m square. So instead of this rho u square, I can write gamma p m square. Is that clear?
Yes, sir.
Yes, sir.
Okay, so substitute, then rearrange normal simplification only. Finally, you will get this p2 by p1 in terms of m1 square, m2 square. Okay, in between step, I'm just skipping it. Normal simplification only. Okay, so instead of rho 1 u1, I'm taking gamma p1 m1 square. Then rearrange, take p one side. Okay, in that normal simplification, you'll get this term. This clear, right?
Yes, sir.
Then next one. Okay, thank you. So next one, t2 by t1. So simply I'm going to use, this is wrong I think. Simply I'm going to use p is equal to rho rt. So apply here. You will get p2 by p1 is equal to rho 1 t1 divided by rho 2 t2. So what I need is t2 by t1. Sorry. Okay, so what I need is t2 by t1. So this time you should take it to the left hand side. So you will get p2 by p1 into rho 1 by rho 2. Is that clear? P is equal
Yes.
to rho RT. RR will get cancelled. So remaining rho 1 by rho 2 another side. And instead of this rho 1 by rho 2, I am taking u2 by u1 because from the continuity, I can rearrange like that. That is rho 2 you take this side, u1 you take this side. So you will get rho 1 by rho 2 is equal to u2 by u1. So instead of this rho 1 by rho 2, they have taken u2 by u1. Okay. So first we got in terms of pressure and density. Then we have written in terms of pressure and velocity. Again, I don't want this velocity term also. So we know m is equal to v by a. So v is equal to ma. So instead of this u2, I can write m2 a2. Instead of u1, m1 a1. Again, this a1 also I don't want. Okay, so I know a is equal to root of gamma rt. Okay, substitute here gamma r, everything is constant. So remaining I will get root of t2 by t1. So first using p is equal to rho rt, this term. Then using rho 1 u1 is equal to rho 2 u2. So this term. Then u is equal to ma. So this term. Again a is equal to gamma rt. So this one. Now you see t2 by t1 in terms of p2 by p1, m2 m1, t2 by t1. Okay, I can take this t2 by t1 this side, and I know p2 by p1 in terms of m1 m2. Here already m1 m2 is there. Rearrange, you will get this equation. Is that clear?
Yes, sir.
Okay. Then third one is density. Again, we can use the same p is equal to rho rt. Okay, so rho is equal to p by rt. So P2 by P1 into T1 by T2. So already both we have found in terms of Mach number. Substitute and simplify. We will get this equation. So all those formulas, it will be available in the gas table. Okay, so all static properties are over. Now we can go to the stagnation. So I should find P02 and P01 relation. See here the flow is isentropic. Okay, I know M1, P1, even I can find P01. Here flow is isentropic, and inside the duct the flow is non-isentropic because of the heat transfer. Again, outside it is isentropic. Okay, M2, P2, P02. So in this isentropic station, using isentropic relation, I can find P01 by P1. Okay. Similarly, in the station 2, I can find P02 by P2. And across the duct, just now I found P2 by P1. So using these three, I am finding P02 by P01 ratio. So P02 by P2, P01 by P1 into P2 by P1. Using these three ratios, okay, I am finding P02 by P01 relation in terms of Mach number. Is it clear?
Yes, sir.
Okay. So almost same procedure for this temperature also. So in this station I can find T01 by T1. The station 2 I can find T02 by T2 using isentropic. Then inside it is non-isentropic. So here I know T2 by T1. Use this three relation. You can find this ratio. So finally you can get in terms of Mach number M1, M2. That's it. Derivation part for the Rayleigh flow. So all the equation will be available in the gas table. So this is very, very important. Q is equal to Cp T02 by T01. Then P2 by P1, T2 by T1. Everything in terms of only M1, M2. Okay. Rho 2 by rho 1, P02 by P01, T02 by T01. So once you know M1 and M2, you can find all these static and stagnation properties. So here I explained how to solve the problem using the formulas. Actually, we have two methods. So in one method, if you want to use the formulas, then this procedure you have to follow. But what will happen? Mostly we don't use this procedure. We will go for the method where we will use the gas table, because this will take more time if you manually calculate. But still, I'll explain. Okay, how to solve the problem using the above relations we have derived. So normally in the problem they will give M1, P1, T1, rho 1, etc. in the station 1. Also they will give what is the Q value, whether it is heat addition, rejection or something they will mention. Okay, this will be the known parameter. So our first step should be, for this M1 we should go to the isentropic table and we should find T01 by T1, P01 by P1. Okay, because here you can apply the isentropic relation. Here also isentropic, only in between it is non-isentropic. Okay, first step, using M1 I can find P01 by P1, T01 by T1. So I know P1 T1, so that I can find T01 P01. This is clear, right? A normal procedure.
Yes, sir.
Okay, then second step, we will use this formula. So we know Q value, we know T01 value, Cp for the air we know that. So from this I can find T02. So using this formula I am going to find T02. This is my second step. Then third step, so I know both T01 and T02. So I can find this ratio, and in this formula I know what is gamma value, Mn value. Then solve it, you can find M2. This is the third step. Is it clear?
Yes, sir.
So once I know M1 and M2, substitute in these relations, I can find all the static stagnation properties. P2 by P1, T2 by T1, rho 2 by rho 1, P02 by P01. That's it. Any doubt here in this procedure?
No, sir.
Okay.
No, sir.
Okay. So this is the fourth step. So no need to repeat it, right? I will go to the next step. So that's why I said this formula is compulsory. Without that, we cannot find this T02. Okay. So once you know these two, then we can go for this relation and find the M2. So once the Mach number is known, we can find everything. But mostly we don't use this method, because you see this T02 by T01, lot of square term. Okay, so to solve this, it will take more time. So mostly we don't go for this formulas. But okay, so next step. So we are adding some heat or we are removing some heat. So we should know how the properties are changing. Okay, so we may take subsonic, we may take supersonic. So by adding and removing the heat, how the flow should changes, that we should understand. For that, we are going to solve two problems. First problem is for the subsonic case. Second problem is using the supersonic case. That's what here they have solved. So the first problem, they have taken the supersonic Mach number zero point 0.2. They are given pressure, temperature, even Q value 1 into 10 power 6 joule per kilogram. Everything they have given. Okay, Mach number, pressure, temperature they have given. They solved it using the procedure just we have discussed. First isentropic table T naught 1 P naught 1. From that T naught 1 P naught 1 value, then Q is equal to Cp T naught 2 minus T naught 1. From that T naught 2 value, once you know these two value, find the ratio from that M2. So once you know M1 and M2, you can find all other ratios. That's how they have solved it here. Now from this value, we will see how the Mach number and other properties changes. See, we have taken the Mach number 0.2, and because of the heat addition, it is accelerated to 0.58. Okay, from 0.2 to 0.58 it is increased, and clearly there is a heat addition. So definitely T01 and T1 will increase. So T01 is 275. Due to the heat addition, it is increased to 1270. Okay. Similarly, T1 is 273. T2 is 1183. Okay. So T0 and T will increase due to the heat addition. So Mach number also increased, temperature also increased. Next one is pressure. You know the relation between pressure and velocity. Okay, if pressure decreases, that is velocity increases, pressure will decrease. So here acceleration happened, so that P1 is 1. Okay, but P2 is less than 1 because of the flow acceleration. So pressure alone decreased. Is it clear?
Yes, sir.
Okay. So this is for the subsonic. Now we will go for the supersonic. So here they have taken Mach number 3, and the Q is 3 into 10 power 5 heat addition. Okay, P1, T1 also given. See, for the Mach number of 3, it is decelerated to 1.58. Okay, in the subsonic it is accelerated, in supersonic it is decelerated. Of course, if velocity decreased, definitely this pressure will increase. So here 1 atm, here 3 atm. Okay, but again here also heat addition, so T0 and T will increase. So T1 is 300, T2 is 761, and T01 is 840, T02 is 1139. Okay, so these two increased. Is it clear? Have it changed?
Yes, sir.
So now we will summarize subsonic and supersonic flow case. So we have taken Mach number 0.2, and it is accelerated to 0.58 in subsonic case. And in the supersonic, so we have taken Mach number 3, and it is decelerated to 1.58, I think. Okay. So subsonic means flow got accelerated due to the heat addition, but in the supersonic flow, the flow got decelerated. Okay, and you can ask how much maximum we can accelerate in the subsonic. So maximum this side we can accelerate to sonic. Okay, after that choking will occur. Similarly, the supersonic also, if you keep on adding the Q further, this 3 can be maximum decelerated to 1. After that choking will occur. Okay, so for this Q1 value, it increased to 0.58. If we further keep on increase the Q value, it will keep on accelerating, and maximum it can reach 1. After that choking will occur. Is it clear?
Yes.
So now I can draw one common control volume. So whether the flow is subsonic or supersonic, this side I can maximum get 1. Okay, that means subsonic flow will get accelerated, supersonic flow will get decelerated, and maximum it can reach 1. Is it clear?
Yes, sir.
Yeah, so that's it. So in both the cases, T by T naught is increasing, subsonic and supersonic, and in both the cases, there is a stagnation pressure loss. Okay, and subsonic means acceleration, so static pressure decreases. Supersonic means deceleration, so static pressure increases. So both flow will move towards the sonic if you keep on adding the heat. So this is the important point. Shall I go to the next slide?
Yes.
Sure, sir.
Okay. So this is the Rayleigh table. So for the Mach number, they used to give P by P star, T by T star, P naught by P naught star, T naught by T naught star values, even rho by rho star, etc. But what we have derived is P2 by P1, T2 by T1, T02 by T01, P02 by P01. This only we have derived. Okay, but here we have P by P star. So here we have static relation. But in the gas table, they related static and sonic. So now I will explain how to convert this equation to the static and sonic. Okay. So once you know the M1 from this table, you can find P1 by P star, T1 by T star, like that. All the property you can find it. Okay. So I will use this control volume to explain that. Assume initially I am taking Mach number 0.2, and due to the Q1 value, it is accelerated to 0.58 in the first problem. Okay, and if I further add the heat, for example Q2 value, then this 0 0.8 can be maximum accelerated to 1. Okay, so 0.2 is okay. If I add Q1 plus Q2, this 0.2 can be accelerated to 1, or this 0.58. If I add Q2, it can also accelerate to 1. Like that, I can take any arbitrary station in between that, and all those things can be accelerated to 1 by giving the proper Q value. Is that clear?
Yes, sir.
So by giving the proper Q value, so all these station properties can be maximum accelerated to 1. Similarly, if you take supersonic, by giving the proper Q value, all the supersonic value can be decelerated to 1. So instead of this control volume, I am taking this. That is, so I am taking any arbitrary station and the sonic station. That alone I have mentioned in this control volume. Okay. So instead of two static stations, any one arbitrary static station, then sonic station, because everything can be converted into one. So this any arbitrary station I am taking as the station 2. So I am taking property as M, P, T, rho, like that. Okay, and the sonic station I am mentioning as 1. So M is equal to 1 means then the corresponding property will be P star, T star, rho star, etc. So this is my final control volume. Because all the stations can be related to the M is equal to 1. This is clear, right? This final control volume.
Yes, sir.
Okay. So now, so this is what already we derived. P2 by P1, T2 by T1, etc. and all. Now I have converted that control volume to static and sonic. So in the station 2, instead of M2, I can have M. Instead of T2, I have T. Instead of P2, I have P. Instead of rho 2, I have rho. Instead of P02, I have P0, like that. But in the station 1, instead of M1, I have 1. Okay. And instead of T1, I have T star because M is equal to 1. And instead of P1, I have P star. Instead of P0, I have P0 star. Like that. Here everything is star properties because of the sonic. Now apply this equation to this control volume. So if you apply, so instead of P2, I will simply take P. And instead of P1, I will take P star. And instead of M1, I will substitute 1. And instead of M2, I will substitute only M. So that you will get P by P star is equal to 1 plus gamma divided by 1 plus gamma M square. Is that clear?
Yes, sir.
So this is how in the gas table they converted all the stagnation, stagnation to static sonic and stagnation sonic, like that they have converted. So now we have both formulas which relate static, also static and sonic. And using this formula already we discussed how to solve the problem, but it will be a lengthy procedure. We don't go for the formulas to solve the problem. So mostly we will use gas table to solve the problem. Now I will explain how to use this gas table to solve the problem. Procedures are almost same only. Maybe I'll explain once again that using formulas. So first I have taken M1, go to isentropic table. We can find these two ratios. So we know P1, T1, we can find P01, T01. Then we have taken this second equation, Q is equal to Cp T02 minus T01. So Q T01 is known, from that you can find T02. Then third step, using this big formula, so we know T02, we know T01, and also M1, substitute you will get M2. And once you know M1, M2, you can find all other properties. This is using formula, but it is a lengthy procedure, we don't use it. Now we will come to the gas table, how to solve the problem. So again, the first two steps are same only. So they will give M1, P1, T1, also the Q value. So your first step should be, for that M1, you should go to the isentropic table. You should find these two ratios. Okay, M1, T1, P1 is known. You can find T01, P01. Then second step, using this Q formula, you know T01, Q, Cp, etc. You can find the T02. So this is common. Then third step, for this M1 itself, you should go to the Rayleigh table. Okay, and from the table you can find these ratios. For example, if this is M1, you will get P1 by P star, P01 by P0 star, T1 by T star, T01 by T0 star. All this you can find it. Okay, third step is different. For the same M1, previously you checked isentropic. Now you have to check the Rayleigh table. Okay, so you will get all these ratios. So we know already what is P1, T1, P01, T01. So substitute, you can find all the star properties. Is it clear? Third step.
Yes, sir.
Okay. And so I have said I have taken 0.2, here 0.58. By adding Q1 and Q2, it can be converted into 1. Okay. Or this 0.58 also, using Q2, it can be converted into 1. Okay, so here property may be P2, T2, rho 2, M2. Here may be M1, P1, rho 1, T1. You see, this M1, P1, rho 1 can be related to this P star, T star. This P2, T2, M2 also can be related to P star, T star. So for both station, this P star, T star are common. Okay, only P1, P2 is varying. This P star, T star is common. Okay, is it clear? The star properties
Yes,
are
sir.
common for any arbitrary station. Okay, so we found P star, T star, P naught star, T naught star. Then the fourth step will be, so I know T naught 2 from this equation I found it. I know T naught star which is constant. So using this T naught 2 and T naught star relation, I can use the same Rayleigh table. I can find remaining properties. That is M2, P2 by P star, T2 by T star, P0 by P0 star. So already we found the star properties. From that we can find P2, T2, P02, etc. and all. That's it. Is that clear?
Yes, sir.
So totally 4 steps. The first isentropic, next this equation, then Rayleigh table, here also Rayleigh table. Okay, so once you know the M1, immediately you should go to the isentropic and write the ratios. Then immediately you go to the Rayleigh table and find all these ratios. Okay, this should be your first step. Then you can use this, you can find T naught 2, then T naught 2 by T naught ratio, you can find remaining properties. Okay, here they solve the same problem using the gas table. See, once they know the Mach number, say they found these two ratio from the isentropic table. Okay, then second step using the Q formula, they are finding the T naught 2. Okay, then third step for the same M1, you have to go to the Rayleigh table. You can find all the star properties. Then once you know T naught star and T naught 2, from that ratio, again Rayleigh table, we can find all other ratios and values. Just procedure alone they have shown. Okay, so now some concepts involved in this Rayleigh flow we will discuss. So here I have taken the subsonic problem as example. So initially I have taken 0.2 this side and I have added Q value of 1 into 10 power 6 so that my flow got accelerated to 0.58. Now assume I am keep on increasing that Q value. So instead of 1 into 10 power 6, this time I am increasing to 4 into 10 power 6. Now I already told you subsonic flow will get accelerated due to the Q. Okay, and maximum it will reach 1. So assume for this 4 into 10 power 6, the flow got further accelerated and reached Mach number 0.8. Okay, then further I am increasing the Q. This time it is 6 into 10 power 6. Assume we are getting the maximum Mach number 1 for this 6. Okay, so once it reached to 1, then choking will occur. So we cannot increase this Mach number more than 1. Okay, so it is keep on increased 0.5, 0.8. Now it is 1. So we cannot increase this further because this is maximum. Choking occurred. This is clear, right?
Yes, sir.
So once the flow got choked, that is Mach number reached to 1, then I can take this Q value as Q max. Okay, I can give different Q value. So once the choking occurred, I am taking the corresponding Q as Q max. And this is S max, that is entropy. So I already told you, due to that heat transfer, there is a stagnation pressure loss. Okay, if there is a stagnation pressure loss, then there will be increase in entropy. So for every adding of Q, there will be increase in entropy. S1, S2 like that, entropy also will keep on increase. And the entropy corresponding to the choking, I am taking as S max. Is that clear? Q max, S max.
Yes, sir.
Okay. So now we reach the choking condition. Okay, this side it got flow got choked, and already we got Q max value. Okay. Now assume I'm further increasing the Q value more than Q max. Maybe instead of 6 into 10 power 6, this time 7 into 10 power 6. So this side it's fixed. It cannot go beyond it because already choking happened. So in that time, how nature will adapt? So what they have observed it, there is a propagating pressure waves in the upstream direction, so which changes the region, that is flow region next to the inlet. So due to this pressure propagation upstream, this inlet Mach number is further reduced. Okay, so for Q max it reached to 1. If I further increase, this side we cannot increase. Okay, this is fixed. In that case, nature creates the propagating pressure wave in the upstream direction, which alter the subsonic inlet condition, that is reduces the Mach number. Okay, see already this side it is fixed, so we are getting the same Mach number. Instead, this 0.2 is further reduced to 0.15. If I further increase to 10 power 6, again this side it is fixed, 1 will not vary. This 0.15 may be reduced to 0.1. Like that, it will keep on changing. Is it clear for subsonic?
Yes, sir.
Okay. So whenever you are giving Q value which is greater than Q max in the subsonic condition, there will be a propagating pressure waves that will reduce the inlet Mach number. This is important point. This for subsonic. Now we will see it for the supersonic. Then we can take a break. And this is for the supersonic. So initially we have taken Mach number 3 due to the 510 heat addition. It decelerated to 1.58. Again there will be increase in entropy. So like that I am keep on increasing the Q value. Assume for the Q value of 110 power 6, I am achieving M is equal to 1 in the exit. We know the corresponding entropy is S max. This is clear, right?
Yes, sir.
Okay, so now further I am increasing the Q value, that is Q greater than Q max. Okay, so Q max is 110 power 6. Now I am adding 2 into 10 power 6 more than Q max. Again, this side it is fixed. Okay, we cannot decelerate further. So this side we have Mach number 3. It keep on decelerated. Finally, we achieved one choking occurred. So now I am adding Q value which is greater than Q max. This side it is fixed. We cannot change it. And this side also it is a very high momentum flow. Okay, because supersonic flow, right? So there is no possibility of pressure wave propagating in the upstream because very high momentum flow. So the upstream propagation is not possible. So this also almost fixed. So we cannot alter this supersonic. So sonic also we cannot alter. Supersonic also we cannot alter. So the nature adopt a different method here. What happens if I increase the Q greater than Q max? For example, instead of 2 here I have taken 410 power 6. Let me clear. Okay, so this is Q greater than Q max values. What I am explaining here. So assume I am taking 410 power 6. Okay, so our Q max is 110 power 6. Assume this is the Mach number distribution. So this side I have Mach number 3. This side choking occurred. Maybe I'm getting the Mach number distribution like this. Okay, Mach number contour. So what will happen for the Q greater than Q max? There will be a normal shock inside the duct. Okay, so assume here I have Mach number 1.5. That normal shock will convert supersonic Mach number to subsonic Mach number 0.9, and we are adding the heat throughout the duct. So what will happen? The subsonic flow will get accelerated and it will reach 1. Is that clear? So
Yes, sir.
it adapt the condition by creating the normal shock. Okay. So further I'm increasing the Q value. Instead of 4, this time it is 6 into 10 power 6. So what will happen? That normal shock will move towards the inlet direction. Assume here also this is the Mach number distribution. Now the shock wave is moved to here and it converts assume 2 to Mach number 0.7, and there is a heat transfer throughout the duct. Then this 0.7 is accelerated to 1. Okay, I'm further increasing the Q value to 8 into 10 power 6. Then the normal shock is further moved here. Okay, these are all the Mach number distribution. So on the normal shock getting stronger. Okay, when it is moved towards the inlet, it getting stronger. You can see by seeing that values 1.5 to 0.9, and here 2 to 0.7. Okay, compression is increased. Now see 2.5 to 0.5. When it is moving in this direction, the normal shock becomes stronger. So much compression happened. So Mach number 2.5 to 0.5. Then heat addition, the subsonic flow got accelerated and reaching 1. So that backside it is always 1. Only this normal shock forms inside and changes the flow condition inside it. So this side also Mach number 3, it is fixed. Is it clear?
Yes, sir.
So this is how the flow adjusts for the Q greater than Q max for subsonic and supersonic. Sorry. So I'll just short revise it. So for subsonic means for Q greater than Q max, that is after choking, there will be a propagating pressure wave in the inlet which reduces the inlet Mach number. This is first case. Then if it is supersonic, both side it is fixed after choking. What will happen? There is a normal shock wave, and by keep on increasing the Q value, the normal shock will move towards the inlet and it is getting stronger. That's it. So next one is Rayleigh curve. Okay, this Rayleigh curve is drawn between enthalpy and entropy. Okay, enthalpy is in y-axis, entropy in x-axis. So this is the heating direction. Okay, and this is the static enthalpy curve for Rayleigh flow. Okay, that is different H value for different S entropy. And you can see the top one they named it as subsonic, this bottom one they named it as supersonic, and this is the M is equal to 1 point. You can ask why this is taken as subsonic, why this is taken as supersonic. Why can't we mention this is supersonic? Okay. So for example, assume there is a Mach number 0.2 which is accelerated to Mach number 3. Okay. So this is low Mach number. So definitely temperature, pressure, everything will be higher. But this is accelerated to Mach number 3. So temperature, pressure, everything will be lower. Okay. Compared to this subsonic, here temperature, pressure, everything will be lower. Assume T1, T2. Okay. If we know the relation between H and temperature, H is equal to CPT. If T1 is higher, H1 also will be higher. If T2 is lower, H2 also will be lower. Okay, that's why these are all different H value, right? So subsonic H values are higher and supersonic H values are lower. So this is subsonic curve, this is supersonic curve. Is it clear?
Yes, sir.
Okay. So this is static H value for different entropy, and this is M is equal to 1 line, 1 point. And initially in the subsonic case, what happened? Assume we have taken subsonic Mach number of 0.28. By adding Q1, it is accelerated to 0.58, and like that by adding the Q maximum, it can accelerate to 1. Okay. For example, for Q max value, that 0.28 is accelerated to 1. And if I further add Q, which is greater than Q max, what will happen? There is a upstream pressure propagation. So this 0.28 is reduced to 0.15. If I further increase, this point may be further go to the left hand side, 0.1. Is it clear? How the curve varies for different Q value?
Yes, sir.
Okay. So this is for Q max, and for more than Q max, this point alone will go in the left hand side. This is for the subsonic. Now we will go to the supersonic. In the supersonic case, we have taken 3. Okay, I will take one example also. This side I have 1. Assume this is the Mach number distribution. Okay, assume maybe normal shock is standing here. So 3 to 2. The normal shock convert to 0.7. Then 0.7 again accelerate to 1. Like that I am getting one flow field. For this, how to draw the Rayleigh curve we will see here. See, assume my Mach number 3 point is here. Okay. Then due to the heat addition, my Mach number is reduced to Mach number 2. This is clear, right?
Yes.
Then there is a normal shock which convert Mach number 2 to 0.7. Okay, then for the 0.7, I should mark along this line, the subsonic line, I should mark it. Maybe I will take one reference line here, even some reference points also, point A, point B, point C, like that. So can you tell where can I point the this Mach number 0.7? whether it is on the A or B or C. Can you guess? Normal shock convert Mach number 2 to 0.7. Now that 0.7 somewhere on the subsonic line I should mark it. So can you guess at which point we can mark it? So we know across the normal shock, okay, there is a stagnation pressure loss across the normal shock, that is P02 is reduced. So entropy is always increases across the normal shock. Okay, then I should take this C point so that you can see between these 2 points there is a del S increase in entropy. Even I should not take this straight point. If you take it, that means entropy is constant. But across the normal shock, entropy is increasing. It is not constant. Entropy increases due to the stagnation pressure loss. Is that clear? So always across the normal shock, entropy is increasing. So you should mention the subsonic point using the inclined line, okay, which is inclined in the right hand side. That is right side of this reference point. Okay, so this is my 0.7. Then the 0.7 is further accelerated to sonic. Is that clear?
Yes.
Okay. So from 2 to 0.7, then 0.7 to 1. Like that, we are getting the curve. So here I have mentioned the stagnation curve also. So you know the relation between stagnation enthalpy and static enthalpy. Okay, just energy equation. H naught is equal to H plus V square by 2. So H naught minus H is equal to V square by 2. Okay, for example, so this is my stagnation curve, subsonic, supersonic. So here I have H naught, here I have H. Due to that difference, I am getting V square by 2 subsonic velocity. Similarly, this is my H naught supersonic. This is my H supersonic. Due to the difference, I am getting V square by 2. You can see the magnitude, very small velocity. Supersonic means very higher. So then we will go to the problem. So problem procedure already I told you, 4 steps. Once you know M1, you go to isentropic, also Rayleigh table. Then using this formula T02, then you find the T02 T02 ratio, another one Rayleigh table, you can find remaining properties. The same thing you are going to apply now. Okay, this is my first problem. So I have two duct. Initially there is a divergent duct, then there is a constant area duct. So they have given pressure, density, temperature, Mach number, area in the duct 1. So I know pressure, density, temperature, Mach number, area. Also they have given Mach number at the station B, and I have to find area in this station 2, pressure, density, T naught value, then Q value. Okay, these are all my unknown. This area, pressure, density, temperature, and this Q is my unknown. So here how to proceed? So your first step should be identifying the Mach number. So even you can split this into two separate duct. Okay, first let's take the first duct. So here I have Mach number 0.68, and you know in the subsonic, if you keep a divergent duct, it will act as a diffuser, right? Because all the commercial subsonic aircraft will use the convergent nozzle to accelerate the flow. If you keep a divergent duct in the subsonic, definitely it will be decelerated. That's why from 0.68 to 0.25 it is decelerated. Is that clear?
Yes.
Okay. And they have mentioned heat transfer only in the second duct. There is no such heat transfer in the duct 1. So I can say here the flow is isentropic. Okay. So here the flow is isentropic. Only here the flow is non-isentropic. So now can you tell how to find area and the station, area, pressure, temperature? How to find it? These are all known. These are all unknown. How to proceed? Okay, so you can find PA by P naught, TA by T naught, even AA by A star, right? From the isentropic table.
Yes.
The next step for this MB also using the same isentropic table, you can find PB by P naught B, TB by T naught B, AB by A star, you can find it. Even if you need only pressure, you can write remaining terms also at the beginning itself. Later it may be useful, otherwise it's okay. It will take just 1 minute to write remaining parameters. So always write whatever the relevant parameter mentioned in the gas table, everything you write it in the given values. Okay. So here they are given PA, TA, even AA. Using that you can find P naught A, T naught A, A star, right? And the flow is isentropic. So T naught A is equal to T naught B, P naught A is equal to P naught B. So I know T naught A, P naught A, T naught B, P naught B, because both are constant. From that I can find pressure and temperature. Temperature is not asked, okay, you can find it. Is that clear?
Yes, sir.
Even A star also I found. From that you can find A, B also. Then only density is remaining. Once you know pressure and temperature, using P is equal to rho or T, you can find the density also. Okay. So now take the second duct, station B, station C. I know Mach number, temperature, pressure, density, area, T naught P, P naught B, everything I know. Okay. And there is some heat transfer that they are asking us to find. So what is the Q value? Q formula?
CP into T naught 2 minus T naught 1.
Very good. Cp T naught 2 minus T naught 1. Actually, I forgot to mention. They are asking us to find the Q value for choking condition. That means what would be the Mach number here?
1.
1. Then how to mention this TC T naught C if it is 1 means?
Star. T star.
Very good. T star and T naught star. Okay. So actually here if you write the exact formula, it would be T naught C minus T naught B. Okay. So T naught B is already found. Okay, because which is equal to T naught A, and T naught C, that is which is equal to T naught star only, we have to find it. That too. So for this duct we found one T naught star, right?
Yes, sir.
But here we are going to find another one T naught star. This is not equal because there is a heat transfer. Okay, here the flow is non-isentropic. You should not mistakenly taken the T naught star, you found it in this isentropic duct. Okay, if there is no Q added in this duct, then this T naught star may be equal. But because of this Q, the flow become non-isentropic. Okay, now we are getting different T naught star. Okay, so you should not take this T naught star. I think now the modified formula is, instead of T naught star we need, instead of T naught C we need T naught star, and instead of T naught B we have T naught A, which is already we found. So this value we know, Cp also we know. How to find this T naught star?
So you can use the Mach number, second Mach number, MB.
MB, then
In the gas table, we have T naught divided by T naught star.
okay. So as there is a heat transfer, you should go to the Rayleigh table. So there you can find PB by P star, PB by T star, P naught B by P naught star, T naught B by T naught star. Everything you can find it. Okay. So we know T naught B substitute. From that you can get T naught star. Is it clear? So this is the problem. So this is completely isentropic using MA and MB. I'm taking all the ratio and finding the all the static properties. Okay, this is normal procedure. Now in the second duct, this is my formula. So here I need T naught star. Okay, so using the MB, go to the Rayleigh table, you can find T naught B by T naught star. T naught B is equal to T naught A. Substitute, you'll get T naught star. So Q is 9.15 10 power 5. See, we have sometime they will ask. So direction of heat transfer, whether the heat is added or removed, that they will ask us to find. So you can find it in two way. One is this Q value, Cp T02 minus T01. Okay. So the overall Q value is in positive, then the heat is added. Is that correct? Because
Yes,
if
sir.
heat is added, this will be more, so it will be positive value. Or sometimes you will get negative value because T02 may be less than T01. So negative means heat will be removed. So using this Q value, you can find whether heat added or removed. This is okay. So next problem. So they have given M1, also P1 value. Then they have mentioned M2. Using that, we should find what is P2, also direction of heat transfer, whether it is heat added or removed. Okay, they haven't asked what is the Q value. They are asking only the direction, whether heat is added or removed. That only they are asking. Here, how will you proceed? So if heat is added or removed, then this will be the Rayleigh flow. Sometimes they won't mention whether it is Rayleigh flow or Fano flow. By seeing that wording, you should find. Okay, so Rayleigh flow, non-isentropic. Now, can you tell how to proceed? So your first step should be checking whether the Mach number is given or not. If the Mach number is given, straight away you should go to the corresponding table. So here I have both Mach number. So I'm going to the Rayleigh table. I'm simply writing what are all the given value. P1 by P star, T1 by T star, P01 by P0 star, T01 by T0 star. Like that I'm going to write all the property. Then I will decide which is required, which is not required. Is that correct?
Yes, sir.
It will take just 1 minute for me to write. Okay. Now from the Rayleigh table, I got all the ratios. Now tell how to proceed.
So we can find P2.
So we can substitute P1 here. From that you can find P star. Okay. And for the Rayleigh flow, any station can be compared to the star. Okay. And the star will be constant throughout the duct. So once I know the P star, I can substitute in this ratio. I can find P2. Is that clear?
Yes, sir.
So this is my first step. P2 is found. Next step, heat transfer. So two way you can find it. One is using this formula. Another one is using the ratio. Which should be appropriate for this problem. Finding the heat transfer direction.
Sir, the ratio.
So second one, huh? The ratio. Okay, you said ratio. How to find the ratio?
So we have T01 by T0 star and T02 by T0 star.
Okay, very good. We have these. So we have these two ratios. So I can write T02 by T0 star, T01 by T0 star. T0 stars are constant. Okay, so from this I can get T naught 2 by T naught 1, and if it is more than 1, heat is added. If it is less than 1, heat is removed. Is that clear?
Yes, sir.
Okay, now we will see. So actually, so instead of finding P star, then P2, straight away they use this formula because we know M1 and M2. Straight away you can substitute and you can find P2 by P1. Like that they found it. Okay, using the formula. But you can use the gas table also. This is just another method they used. This clear, right? Finding P2.
Yes, sir.
Then they are finding these two stagnation temperature ratios. Then T naught 2 by T star, T naught star, T naught 1 by T naught star. Using that I am getting 0.719, which is less than 1. So less than 1 means cooling. So here there is a cooling, removal of heat. Hmm? Or sometime you can say, sir, this is Rayleigh flow. This side I have Mach number 1.5. This side I have Mach number 3. If there is a heat addition, then the supersonic will be decelerated towards 1. Here acceleration happened. That means this should be the cooling. Like that also you can write it. Is that clear?
Yes, sir.
So heating will decelerate, cooling will accelerate the supersonic. So in this problem, they haven't mentioned whether it is Rayleigh or shock wave, nothing they have mentioned. Okay, simply they mention Mach number, temperature in the station 2, temperature in the station 1. So my suggestion is, first step we should draw the control volume. Okay, so here I have M1, here I have M2. So what they have given is M2 and T naught 2. These two values given. Even T naught 1 is given. What they're asking is M1 and P2 by P1. So I don't know whether it is heat transfer or friction or normal shock, anything. But you can see by comparing these two temperature. Okay, so T naught 1 is 100. T naught 1 is 100 degrees Celsius. T naught 2 is 300 degrees Celsius. Okay, in this aerodynamics too, mostly we have normal shock, oblique shock, friction, Rayleigh. In all the cases, if you take normal shock, oblique shock, then Rayleigh, then Fano, friction. So in this case, T naught is constant for normal shock. Oblique also normal T naught is constant. For friction also, there is no heat or removal, T naught is constant. Only in this Rayleigh flow, T naught is not constant. It will increase or decrease. So by comparing this T naught itself, I can find it which it falls in the Rayleigh flow. Is that clear?
Yes, sir.
So like that you can find it, even though they have mentioned whether it is Rayleigh, normal, oblique, Fano. By comparing the T naught, I can find it. Okay. So this is the Rayleigh flow. So what should be the first step? How will you find this P2 by P1? First step, you should see whether any station Mach number is given. So in the station 2, Mach number is given. If I know the Mach number, I can go for the gas table and find the remaining property. So I know M2. Straight away go to the Rayleigh table. You can find just whatever the value is available. Now, next step. Very good. So first step maybe from this ratio, I know T naught 2 value. Substitute, you can find the T naught star. and T naught star is constant everywhere. So I know T naught 1, I know T naught star. Okay, I know T naught 1, I know T naught star. So again, I can go to the same Rayleigh table. I can find M1 P1 by P star, T1 by T star, P naught 1 by P naught star. So we have P2 by P star, also P1 by P star. From this ratio, I can find P2 by P1 value. Okay, so M1 is straight away we can get it from the table. Then using these two ratio, I can find P2 by P1. So first they are going to the Rayleigh table. For Mach number, they are finding T02. From that you can find T0 star. Once you know T0 1, T0 star, you can find the ratio. Again, using the Rayleigh table, you can find M1. And once you know M1 and M2, manually they are substituting and finding it.